Well, thank you for the invitation to share our work in this workshop. My name is Karina Ramos Musalem, and I'm an assistant professor at the Institute for Atmospheric Sciences and Climate Change at UNAM in Mexico City. And I'll talk about some work I have been doing with Bruce Cornwell, Sarah Gill, and Matt Maslow and at Scripps. And it's about the influence of coastal topography on the generation and propagation of coastal trap waves, a case study. Oh, it's not changing. There you go. Okay, there are these two questions that we were asked to answer today. So from our perspective, I guess the answer to the first one is that seafloor pressure observations are important because they provide a direct way of measuring wind and other forcing along the coast through the inverse problem. And they also carry information about the coastal wave guide that we have seen. For the second question, I'll show you an example of topographically induced modifications to the generation and propagation of CTWs after a wind event in Southern California. Okay, so there's a little caveat or a little note. I'll talk about signals in timescales that are lower than, let's say, 3 days. So let's keep in mind that the waveguide can send waves at all timescales, right? And so high frequency measurements would be good for us to understand the waveguide, and hypothetically, that could help the predictions or our predictions at lower frequencies. Okay, so to answer the first question, let me first distinguish between two kinds of models in general. First, we have the regular forward perturbation models. So these are the more common ones where, for example, say we have wind blows over the ocean. So this would be a perturbation. And then we see how the system evolves, right? And so these models show us where and when the system responds to a specific perturbation, in this case, the wind blowing. On the other hand, we have adjoint models, which show us where and when perturbations in the model forcing would lead to a specific response, right? So for example, if we choose a variable, say sea surface height, and evaluate all processes affecting sea surface height, this could be winds, eddies, currents, topography, we've seen a bunch of them, stratification, and quantify their contributions to explain and predict observed sea surface height variability, right? So in a way, adjoint models solve for sensitivity. So they tell us what model inputs are capable of making just a particular change that we observe or that we measure. And here's an example from Ariane Verdi and collaborators in 2014. Here they used an adjoint model to find the sensitivity of sea surface height at Port St. Louis, which is located around here, to different forcing. And in particular, we see here sensitivity to a longshore wind stress. And so these maps show the wind stress forcing that can drive the coastal sea surface height response at Port St. Louis. And so here, a positive sensitivity implies that a positive wind perturbation at that location, so anywhere in the map that we look, will cause a positive change in sea surface height at Port St. Louis, which is the place they were analyzing. And so this model allowed them to find an unsuspected remote forcing region in Sebastián Vizcaíno Bay, which is this bay in the Baja California coast. And in a way, it was expected that sea surface height would have obviously a fast response to local wind stress, but they found that that remote winds in the bay also generate a response, and a quite fast one in Port St. Louis, right? So this is the response can be seen in about between an hour, we see here, to up to 12 hours. But so what is the connection to seafloor or to bottom pressure? Well, bottom pressure observations give us a direct way of measuring kind of the effective wind along the coast through the inverse problem, right? So we can invert for wind stress and many other forcings, doesn't have to be only wind stress, from pressure measurements. And this not only improves our understanding of processes, but it also improves our estimates of the ocean state, including bottom pressure and atmospheric forcing, of course. So now, as for the second question, what processes cause a variation of seafloor pressure? Here's an example, and this is a problem that we have been working on for a little bit now, and it's motivated by the findings of that apparent relevance of winds blowing in Sebastián Vizcaíno Bay as a remote forcing region for sea surface height variability in general in Southern California. And so in particular, we want to know what is the effect of Sebastián Vizcaíno Bay on the waveguide along the coast, right? And so this is the model domain. to answer this question, we use an idealized configuration of the MIT GCM model. And I just want to be clear that this is not a joint version. This is a perturbation model where we have runs with realistic topography and coastline. And I'm showing them here at the bottom. And we compare them to runs without debate, right? So we force the model with a long-shore wind event, very simple, which is more like a wind burst than an actual wind event. That lasts for 3.5 hours, and we see what the response of the system is. And the model is stratified, but density is horizontally homogeneous. So this is a very, very idealized model. So now let's concentrate on the sea surface height response along the coast due to the bay. So to isolate the effect of the bay, we see the difference in sea surface height between the run with the bay and the run without the bay, and that's what I'm showing here. This plot shows, so the one that we have here shows in the y-axis, we have all the cells along the coast. So it would be all of these red points. Yeah, and in the x-axis we have the time, right? So these are ordered by distance to the bay. And then remember that the wind event is 3.5 hours, and the simulation runs for 5 days. So that's what we're showing here. And so here we can see that there's a very fast barotropic signal that propagates northward, and it gets amplified around Santa Barbara Channel that we can see here. And we also see baroclinic signals here at the bottom that propagate more slowly and that have lower frequencies. And so looking at the barotropic part of the signal, we saw in frequency spectra that I'm not showing here, it shows that these fast barotropic signals will have an effect in bottom pressure in timescales between 2.2 and 4.6 hours. So these are pretty fast. And they seem to correspond to like sub-basin modes. And here I show the structures of those modes and their principal components. While the slower signals, which are these ones, they propagate as coastal trap waves, the ones that we have been talking about. These are just a bit faster. And here we can see just a snapshot of surface meridional velocity. And here a lower or the more barotropic modes to say in a way, will have an effect on bottom pressure, right? And here's or there is more on this in that amazing paper by Randy Watts in 2021, where they looked at bottom pressure in Cascadia. Right. So just to summarize, to us, I guess an attractive application of seafloor pressure observations is that we can get measurements of effective forcing in the ocean, and this allows us to improve our understanding not only of the physics but also of our models, right? As for the second question, well, I'll just give you an example of a process that can cause seafloor pressure variations in timescales on the order of a few hours, caused by signals that arise just from preserving a complex coastline and realistic bathymetry, really. So with that, I'm happy to answer any questions that you may have.